Martin Bourne visiting from Cambridge, from the IOA. Martin, for the next of the coevolution of galaxies and black holes, particularly has done a lot of work on understanding and modeling AGN feedback, especially modeling it in simulations, 3D, hydro, cosmological, and non-cosmological simulations of galaxies and black holes. He started out with his PhD in Leicester, where his advisor was Sergei Nayakhin, that many of you know from the planet formation side. Sergei has been a frequent visitor in the past year at the Institute. And then after 2015, when he got his PhD, he moved to Cambridge postdoctoral position. And while he was there, he overlapped with Davide Fiacconi, one of our former Institute members. Then he had a pause of a couple of years in industry. And then since last year, he's back in the field, also at Cambridge, at IOA, and also the Carbon Institute. And today he's going to talk about simulating supermassive black holes, accretion, spin, and evolution.
Yeah, thanks, Lucio. Thanks for inviting me to come and talk about a few different projects that I've been working on that span right back to when I was first started in Cambridge back in 2015, working with this group of people down here, primarily with Deborah Siatsky in her group. And yeah, so the main motivation for what we're doing is trying to build, higher resolution, physically motivated models to capture, the evolution of supermassive black holes over cosmic time. And obviously, in the last few years, we've had the first images from the Event Horizon Telescope, first from the black hole in the center of M87, and then more recently from the black hole in the center of our own galaxy in the Milky Way. But as I say, this is only sort of the recent confirmation or imaging of these extreme objects in the centers of galaxies. And before this, in the last century, the first hints came from the fact that you had these extragalactic sources emitting vast amounts of energy as material accretes onto them that were, postulated to be, very efficient engines in the form of black holes to the centers of galaxies. And then also by looking at the impact they have on the dynamics of objects, stars, and gas within their vicinity, you can infer, for example, their masses. And this is how relations like the one on the left here, the M sigma relation that I think is probably in almost every talk about supermassive black holes in galaxies, showing this tight correlation between the black hole mass and the velocity dispersion in the center of the system. And we think that supermassive black holes at least live in the centers of all massive galaxies. There's also growing observational evidence for them in lower mass galaxies as well. And the tightness of this relation, given the fact that actually gravitationally the black holes are very small compared to their host galaxy, is often interpreted as a link between accretion and feedback between the black hole acting on and communicating with its host galaxy. And if we think about the local population of supermassive black holes, we can ask a few questions in terms of how do we get this population? So how do they form? How do they grow, occurring through accretion and mergers? And what impact do they have on their environment? And this can be either through feedback or through their dynamical interaction. For example, in massive ellipticals, if you have a black hole binary, you can end up with scouring that leads to a core in the profile for your elliptical. So today I'm going to talk about the second two of these mostly, and I'm going to ignore seeding for now. So if we think about growing the supermassive black hole population over cosmic time, we know galaxies grow through hierarchical structure formation. So as smaller galaxies merge and form larger galaxies, the black holes that live in their centers are expected to also merge and build up their mass until we have the local population. As this occurs, the black holes can also accrete material and grow their mass through the swallowing of gas, which then couples to feedback. And I quite like this this image here. So this is from the jet in M87. So we had the image of from the Event Horizon Telescope of the black hole in the center of M87. And then we have observations over a range of different wave bands looking at different length scales, illustrating the wide range of phenomena and features that you get within these massive jets, these large jets that are produced from accretion onto the central supermassive black hole. And I think these jets are probably one of the most synonymous forms of feedback from black holes that we see acting in the most massive galaxies. As I said, also there's growing evidence of AGN outflows and jets in other types of galaxies as well, in jets in safer galaxies, which are much harder to see because you don't have this hot halo where you can observe the lobes that the jets inflate, and also observations of AGN, for example, in dwarf galaxies. It's not just in the electromagnetic band. We also have, since 2016, we have these gravitational wave observations of stellar mass black hole mergers from the LIGO observations. More recently, we've started to get the first constraints from the pulsar timing array results looking at the gravitational wave background from merging supermassive black holes. And in the future, we're going to have space-based missions like LISA, again, that will be looking at mergers of supermassive black holes out to very high redshifts, allowing us to put further constraints on how these black holes grow over cosmic time, the properties of their spin evolution as well, which is important for a number of factors, both in terms of what happens during the merger and in terms of how feedback acts and interacts with and shapes galaxy formation evolution. Okay. So when it comes to simulations, this is an example of the buildup of what will be a roughly 10 to the 14 solar mass galaxy cluster. This is from the Fable simulations that were performed in Cambridge by Nick Hendon, who was one of our previous PhD students. And obviously over cosmic time, galaxies merge, you have feedback processes, in particular in these massive systems from the AGN feedback that shape the thermodynamic properties of the galaxy cluster. And they're thought to play a key role, these supermassive black holes, in galaxy evolution for a number of reasons. We get insights of this from cosmological simulations in shaping the high mass end of the galaxy stellar mass function, quenching star formation in massive galaxies, in normalizing the black hole scaling relations, for example, and regulating the black hole growth, and ensuring that the simulations are able to produce realistic looking populations of galaxies. So ensuring that we can not only have these star forming disk galaxies, but also quiescent elliptical galaxies. AGN feedback is thought to help enrich the CGM with metals and redistribute this material within the halos of systems. And as I said, also regulate the thermodynamic state of groups and clusters, which I'll talk a bit about later on. And on top of this, there's also implications or things that we need to understand about the feedback in terms of how it affects the matter distribution, which is important for trying to do cosmology. So this is, for example, looking at the ratio of the matter power spectrum from simulations when you include baryon physics and AGN feedback to if you only have a purely dark matter universe, right? And we can see that in the majority of cases, this is a whole range of different simulations, as well as a few different variations within the Fable model, that quite often you get this suppression in the matter power spectrum. And understanding this is important to be able to interpret, for example, weak lensing observations to try and derive cosmological parameters so that we can try and get to the underlying dark matter distribution. As I say, this is done in a wide range of, AGN feedback is an important ingredient in a wide range of cosmological simulations. This is definitely not an exhaustive list, but again, to be able to produce these wide range of populations of galaxies. But as with any simulation, there's the dynamic range challenge, right? So if we want to form galaxies and capture their buildup, naturally from structure formation, then you want to have some sort of cosmological volume and capturing the processes on this scale. But then if you want to have AGN feedback as well, You have to go through many orders of magnitude in terms of length scale before you get down to processes occurring near the central black hole, governing accretion and production of feedback that then feeds back onto what's happening on the scale of your galaxy and your groups and clusters and so on. And it's not just when it comes to simulations, it's not just a challenge in the dynamic range in terms of length, but also in terms of time. So if you really want to get at the details of what's going on in terms of AGN processes, you have to have much finer resolution in terms of the temporal evolution of your system, as well as looking at much smaller timescales. And so the question is, how can we incorporate these processes within large boxes or within a galaxy formation context? There was this recent plot from the Flamingo simulations illustrating how these large-scale cosmological boxes have evolved over time. And essentially, each diagonal on this plot is a different number of resolution elements. And then we're comparing the size of your box to the mass resolution in gas. And over time, simulations have been able to progress to a high number of resolution elements as computational power and evolution in numerical methods have allowed us to push this limit. But you're still confined essentially to move along one of these lines, either having a big box and low resolution or a small box and being able to have high resolution. This means that when we're doing these galaxy formation simulations, you often have to make simplifications. So a common one, for example, is looking at Bondi accretion. It is using Bondi accretion to look at the black hole growth. And this equation is derived in very idealized circumstances that aren't actually realized in simulations. You also often find this alpha factor here, which is essentially a fudge factor to boost the amount of accretion you have within your simulation, assuming the assumption here is that you're not resolving all of the processes that give you the accretion rate. And also when it comes to feedback, you often have to make simplifying assumptions with how the feedback is modeled, because you're, by necessity, these simulations in big boxes are really sitting on the edge of what's possible numerically. You're injecting your feedback into some low resolution region, and so you have to make simplifying assumptions in how you inject this feedback. And so this is sort of the problem that we've been trying to address with a number of our simulations and works over the last few years. Okay, so all of the projects I'm going to talk about make use of a repo. This is a moving mesh code. So the fluid is discretized on a Voronoi mesh, and this mesh can move essentially with the flow. But you also solve for fluxes between the cells as well. So it's something of a hybrid between your traditional Eulerian and Lagrangian methods. And one of the nice things with this process, you can have somewhat arbitrary criteria for refining and de-refining your cells, so you can focus resolution where you really need it. So one of the early things that Mike Curtis, who was a previous PhD student in the group, developed was what was called a super Lagrangian refinement technique, or a black hole refinement scheme. So essentially, if there's a black hole in the center of this region here, within some refinement region, you gradually force the spatial resolution to improve as you move closer to the central supermassive black hole. And this was originally designed to better capture the gas flows and model the accretion onto the central black hole and resolve the Bondi radius within the systems. But it was also found that in full cosmological simulations, if you include this method, as we have over here, versus when you don't have it, it can also impact the morphology and effectiveness of the feedback, and also the morphology of the cold gas in the center of the galaxy. So in the case where we include it, we end up with this dense star-forming gaseous disk, and also naturally arising bipolar outflow. And this is just coming from a traditional sort of thermal injection of energy within the system. The other model that we've been including, or that we're using in a number of different types of simulation now, was developed by Davide Fiacconi. And this is a subgrid accretion disk model. There are a few of these now developed in the literature, but the idea is that your black hole particle is made up of both the central supermassive black hole, but also a Shikuratsunyaiv or warped Shikuratsunyaiv accretion disk. And you can track, or it tracks both the mass of the accretion disk and the mass of the black hole, and also the angular momentum of the accretion disk and the spin of the black hole, assuming you have Bardeen-Peterson effect torquing the black hole. And then it talks the larger scale simulation through both the mass and angular momentum inflows onto the central particle. Okay. And there's now, I think, a growing number of simulations that are starting to include tracking of the black hole spin as well as its mass, which, the spin's important for a number of different processes, including feedback, but also implications for gravitational wave observations as well. So I'm sure you've probably seen this plot before from the Astrophysics with Lisa paper that's been out over the last year or so. When we have a galaxy merger, as I mentioned, these galaxies have a central supermassive black hole. There's going to be a range of processes acting on different scales, from large scales where dynamical friction is important, that gradually bring the black hole towards the scales where we expect gravitational wave emission to take over and bring the black holes to merger. And one particularly interesting area that we've been looking at is sort of this parsec scale regime, and understanding how you can shrink a supermassive black hole binary in a gas-rich environment. So we've been looking at the evolution of circumbinary disks and how they interact with the binary. So essentially in this context, we have our black hole binary in the center with the large scale disk on, say 10 parsec scales. We have a binary separated by about 2 parsecs. We have mini disks around each of these supermassive black holes. And then below the resolution limit, our resolution goes down to the outer edge of our subgrid accretion disk. We then have the accretion disk model to track both the black hole mass and spin evolution, and try and understand how the spin evolves over the evolution of the binary. And so the area we're particularly been interested in is looking at self-gravitating circumbinary disks. There aren't that many works that have considered self-gravitating disks. I've highlighted in bold a few examples in the list of examples of looking at binary evolution. Just a few things to highlight with the simulations. Again, with the super-Lagrangian refinement technique we can see the difference here, resolving the mini disks and the streams around the black holes and the gas within the cavity. This has an impact on the evolution of the binary and the gravitational torques acting on the binary. We've essentially looked at just a 2 × 10⁶ solar mass binary, circumbinary disk that's a tenth of its mass, and then we've varied mass ratios, tried a couple of eccentricities, and also a few different inclinations. So looking at binaries that are inclined with respect to the circumbinary disk, and also looking at retrograde binaries. Just sort of illustrate the range of simulations we've looked at. So we have this circular ones here. From top to bottom, we've got mass ratios of 1, 1 to 3, and 1 to 10. We have binaries with initial eccentricities of 0.5. We have inclined binaries by 45 degrees, and we have a couple of retrograde examples here. And you can start to pick out different features. The mini disks, for example, essentially in the circular case, essentially fill the Roche lobes of the black holes that we see here, as was suggested way back in 1994 by some early works. But when you have the high eccentricities, you get disruption of the mini disks as the and evolution of the mini disks as the binary moves between apocenter and pericenter. You also see variations in cavity size depending on the mass ratio and the eccentricity, and also whether you're in a prograde or a retrograde system. Where the retrograde case, you end up filling in the cavity. We've looked into and investigated how the torques, gravitational torques, act on the binary. This is important for understanding how the binary evolves, whether we can shrink the binary or on what timescales we can shrink this binary. So here the sort of yellowy purple plots are some average surface density maps, and then the red and blue plots are average torque maps, where the red and blue illustrate positive and negative torques with respect to the central binary. And we can see that from different regions, we get different signs for the torques. And what's really important is the net effect. And the other thing that's interesting to look at is what's happening within the binary orbit. So the location of these mini disks and the ends of these streams feeding these mini disks, and what's happening at larger radii. And so for the prograde cases, we get essentially net positive torques from the material in the vicinity of the mini disks, and net negative torques from larger radii. This is something that's been seen in a number of simulations now. And the question is, how do these balance with each other? And essentially, in all of the cases we get net negative torques acting on the binary. So we always shrink the binaries. And this hasn't been a universal result in simulations. So in other simulations, it's found that the positive torques can outweigh the negative torques and stall the binary shrinking, which is potentially a problem when you're trying to merge these black holes. And the other thing we look at is the effect of accretion, which can effectively torque the binary as well. But this is typically much less important than the gravitational torques within our simulations. Yes, that's right. Yeah. Yeah, so the accretion onto the black hole particles here isn't a traditional sink. We calculate an m dot, an inflow, on the scale of the subgrid accretion disk. Yeah. This is just another way of looking at the gravitational torque profiles. In the prograde, these are all in-plane ones. I haven't got the inclined ones on here. These are all, so the three columns on the left here are prograde. You can see similar patterns. The middle two are eccentric binaries at pericenter and apocenter. But you get these quite sharp features at small radii in the location of the mini disks, which give you a net positive torque. And then you see these much smoother peaks and troughs at larger radii. Some of these are sitting within the circumbinary disk and can be associated with the locations of resonances. But some of the ones at smaller radii are actually within the cavities. And these are really associated with the streams that we can resolve entering the cavity and going down to the black hole. You get different behavior when you have the retrograde binaries here, particularly at larger radii, where you no longer have these smooth features, and you also no longer have consistent location of resonances, because in retrograde binaries you don't expect the formation of resonances within the circumbinary disk, unless, there's some recent work potentially showing resonances if you have an eccentric retrograde binary, but not in the circular case that we're looking at here. The other thing we can consider is the black hole growth. So on here we have a few different things to look at. So the sort of shaded pink and light blue regions, these are the inflow rates onto the central black hole accretion disk, essentially. The solid red and blue are then the mass flow rates that you get from the subgrid model onto the central black hole. And then the green lines are showing the inflow rates, or outflow if it's dashed, through the cavity. And so the material that's going to be feeding the central black hole. So roughly the inflow rates that you get through the cavity are of order the accretion rate onto the binary. But one of the interesting things we see in our simulations that is different to other works is we don't get preferential accretion onto the secondary. So a number of other works have found that the accretion rate onto the secondary supermassive black hole is higher than the primary, because the secondary essentially interacts more closely with the circumbinary disk. There's been a few works that look at, for example, the impact of the thermodynamics of the gas or the viscosity, showing that you can move away from this preferential accretion if you don't have an isothermal equation of state, and if you have fairly low viscosity, which is the case that we have in our simulations, where the viscosity we only include the effective viscosity you get from self-gravity, which is effectively 0.04. And we also have an adiabatic equation of state with beta cooling opposed to an isothermal equation of state, which means the mini disks around the central black holes are fluffier and less robust. And so we get much more fluctuating accretion onto the secondary black hole. This has important impact, implications for the final mass ratio. You're not going to tend towards a mass ratio of 1, and also on the spin evolution of the black holes. So we can think about the spin alignment timescales, which depend on the black hole mass and the accretion rate. And what we've done is we've compared to an analytical model from Gerosa 2015. So if we take the shaded red band and the shaded blue band, these are predicted timescales on which a black hole spin will align with its own accretion disk, assuming preferential accretion onto the secondary as a function of mass ratio. And then this is compared to the dotted green line, which is an analytical expectation for the timescale in which the binary shrinks. We've then taken the alignment timescale from our subgrid model for black holes in our simulations, and also the timescale in which the binary shrinks in our simulations. And we have the red and blue points here, and then also the green shaded band. And because we don't have this preferential accretion, we often find that many of the alignment timescales for the primary are now much shorter, because the primary, if you think about it, if you have preferential accretion onto the secondary, you're restricting the accretion onto the primary. And if you're restricting the accretion onto the primary, you're going to have a longer alignment timescale, which we don't get here, although we do for some of the retrograde cases see suppression for the secondary black holes. But the assumption that you have here is, if you're looking at the timescale in which the spin aligns with each black hole's own accretion disk, and you're interested in whether the spins can align with each other, because when you come to merger, the alignment or misalignment of the black hole spins has an impact on, for example, the recoil velocity of your black hole. Relativistic calculations have shown that you can have very high recoil velocities that could eject your black hole from your host galaxy if the spins are misaligned. This has then implications for gravitational wave detection rates. So while for in-plane binaries, I can just show, yep. All of our simulations, we're seeing that. Yep. So we have, so the stuff that, in the Gerosa model, it was assuming circular. If I remember rightly, it was assuming circular. But we have this band. So the difference between the top and the bottom of this band is related to both whether we're eccentric and whether we're prograde or retrograde as well. Because in the retrograde case, you also get much more rapid shrinking as well. So the top two rows here are for in-plane prograde binaries in this case. And essentially what we find is that the spins are aligning with their accretion disks, and then also aligning with the overall angular momentum of the system. If we then look at our initially misaligned binaries, so this is an example here, the binary is initially at 45 degrees with respect to the second binary disk. And as this evolves over 100 orbits here, we see that the second binary disk attains a warp, and that essentially the angular momentum of the binary and the angular momentum of the second binary disk are acting to align with each other as they torque each other. But what happens is that the mini disks around each black hole, they don't come into rapid alignment with each other. And so, for example, particularly when you have higher mass ratios, the blue dots here are wandering all over the place. And here as well, these are the angular momentum of the mini disks. They don't come into rapid alignment, which means the material feeding the accretion disk and ultimately governing the spin evolution also aren't coming into alignment on such short timescales. So it's not clear when you have initially misaligned binaries whether the spins will align with each other on short enough timescales. Yes, and that's just a quick summary of what I've spoken about in terms of the second binary disks. But I think one of the key things here is that a lot of the simulations that have been done so far on this have explored a very similar sort of parameter space and properties in terms of the thermodynamics of the system. But I think the results can be very sensitive to to how you treat the gas thermodynamics and the viscosity here as well. Okay, I'm going to now shift to a different topic, looking at jet feedback, in particular in galaxy clusters, but this is also applicable for galaxy groups. So on the left here, these are combined X-ray and radio observations of galaxy groups and clusters. In the center, we have Perseus. And I think these systems, when we're thinking about feedback, provide us with, sort of the clearest observational evidence of AGN feedback actually doing something to the environment. You have these radio bright lobes, you have these cavities in the X-ray emission, which is where a jet has inflated a lobe and displaced X-ray emitting material. Interestingly, these lobes seem to be in systems with the shortest central cooling times, although there's probably some observational bias in this as well, because they're easier to see in the systems with the shortest cooling times because you get more X-rays. But also, I think more than that, if you look, you can estimate the power you need to inflate these cavities and compare it to the cooling rates within the halos. You get this correlation essentially between the energy input of the jet and the cooling rate of the large-scale halo, which is often interpreted as showing this sort of self-regulated connection between the heating and cooling within galaxy clusters and the AGN feedback. In this one, yeah, there's these objects here are groups, and then the ones up here are the clusters. Yeah. So the cavity power. So typically, the way this is measured, if from X-ray observations of the cavity, you have the volume. You can estimate the pressure. If you assume the cavity is in pressure equilibrium in the environment, you can say that, therefore, get a measure of the pressure from the environment. So that gives you a PV. So that tells you the work you need to do to inflate the cavity. You have to get a power, you have to have a time scale. There are a few different ways of getting the time scale. Quite often, you can either use the sound speed or say some dynamical time scale for how far the jet's propagated and the expected propagation time for the jet.
Power injected.
Exactly. So then you get an estimate, yeah, from the properties of the cavity. So this is essentially just you get this from the X-ray luminosity, because the X-rays are coming from Bremsstrahlung, so you can then get some cooling rate. Yeah. Okay. So while the energetics seem to match up quite well within these systems, there's still a number of open questions in terms of how the jet actually heats the intracluster medium. So we know that the jets will initially shock heat and inflate these large cavities of relativistic plasma. These cavities will then interact with the environment, potentially driving more shocks and directly heating the ICM. There's potential for these shocks to broaden into sound waves that then propagate through the ICM. There's discussions of mixing, direct mixing of the lobe material, the generation of turbulence, generation of gravity waves, not gravitational waves, as someone confused it with in a talk I gave a few weeks ago. But so these are really fluid properties within the system. But on top of these processes, there's other things that you have to consider. Jets are relativistic. There's going to be magnetic fields. The viscosity and the microphysics of the intracluster medium is going to be important in terms of, for example, with sound waves, where exactly these sound waves dissipate. There's the potential effect of environment and cluster weather, which I'm going to talk about. There's a possible role for cosmic rays, impacts on thermal conduction, how do the jets move and process, and various processes like this. I'm going to talk mostly about the impact of environment and cluster weather. My jets, unfortunately, are not relativistic. This is still very difficult to do in full cosmological simulation, but people are starting to look at this. And I'll also talk a bit about some ongoing work, including magnetic fields as well. And I'm going to shamelessly plug a recent article that Karen Yang and I put out reviewing simulations of jets in galaxy clusters as well. So, yeah, I've already spoken about cosmological simulations quite a bit, and the fact that we have limitations in resolution and how we model jet feedback. so if you're really interested in how jets inflate lobes and how the lobes interact with the environment, this is normally done in more idealized cases where you can focus the resolution and also the time on the details of the feedback. And so what we've done is been developing a model to be able to try and get, accurate lobe inflation, but in cosmological environments. So essentially, this is a model that I worked on back in 2017 now, so quite a while ago. But essentially, using this refinement technique, we can get very high resolution in the center of our galaxy around our black hole. We can inject our jet within some central cylinder. We can take the resolution with the jet, which means that we can capture, these nice high density contrasts, the instabilities. We still have this collimated jet. This is without magnetic fields as well, so this is a purely hydrodynamic jet that we can then try and include in cosmological simulations. Yeah. So we're somewhere in between. So we have this. So yeah, we have this high resolution region, so we can inject the jet into a very low mass. We set the energetics of the region, so the kinetic energy, momentum, temperature of the region, but we don't set a specific density. But what we find happens is that it quickly comes into some sort of pressure equilibrium, and we naturally get a low density jet from this. But yes, you're right. If you want a jet that inflates lobes, it needs to have a lower density than the environment. That's yeah, we get the lobes. We get the lobes because we automatically get an underdense jet once the initial launch starts. That propagates out and gives us these lobes. Yeah. Yeah, so this is just an illustration of different, essentially how we handle the refinement. But essentially, if you have to make sure that you have high enough resolution within the jet to make sure that you don't just stunt the growth of the jet, and you can capture then the lobe inflation to large distances at low densities. And I can just show you an example of this happening. So this is a density plot. We have a density ratio here that's around about 500, if I remember correctly. But this isn't something that we set. So on the left, this is sort of the traditional picture that you would see within an idealized hydrostatic atmosphere, where you inflate the low density jet lobe, and then the jet turns off, and this lobe buoyantly rises through the atmosphere and then eventually succumbs to instabilities. In real galaxy clusters, you're going to have cluster weather, which we see acting on the right here, which is displacing the lobe and acting to disrupt it. Okay. Sorry. So yeah, so the one with substress, essentially we've taken the hydrostatic halo, we've added, I think it's just 10 smaller halos by hand on orbits that just stir the atmosphere. Yep. I realize I'm running short on time, so I'm gonna speed up a little bit. So when we did this, we then did some comparisons with Hitomi, which made some observations of the kinematics in the Perseus cluster. And one of the things we found is that to simultaneously get the properties for the line of sight velocity dispersion, but also the line of sight velocities and the shear, that the sort of diagonal shear that you see within the Hitomi observations, you needed a combination of both the pre-existing cluster weather and the action of the jet. And the jet can't drive significant turbulence outside of its vicinity, and this has been seen in a bunch of other simulations as well. I've got a couple of examples down here, but really the main thing I then want to talk about is the inclusion of these jets in a cosmological environment. So we've taken a zoom simulation of a few times 10 to the 14 solar mass galaxy cluster at redshift 0.1. This was evolved with sort of the traditional cosmological models for feedback, and then we turn on our jet feedback model with the high resolution, and look at the evolution of the lobes and how they heat the intracluster medium. One thing to point out is there's a cold, it's like a few times 10 to the 10 solar masses of what we call cold gas within the center of this system as well, on which the black hole is in the middle of. Here, the lovely mustard and pink is illustrating hot and cold gas, and the green is illustrating jet material. And we can see that this interacts with substructures and cluster weather that's displacing material. So the top lobe is getting pushed because there's some velocity field coming across within the ICM. The bottom lobe interacts strongly with this substructure coming in. This is something of an extreme example of what's happening with this interaction here. We've done this with a few different jet powers as well to get the same sort of qualitative behavior, but the lower power jets are more susceptible to the cluster weather than the high power jets. We can see this velocity field coming in from the top here and pushing the jet lobe across and displacing it. We've had a go at making these sort of mock X-ray and radio images. It's maybe not so clear on here, but getting the X-ray rims and cavities, and then also trying to look at the structure of the jets. This is just an estimate for the synchrotron emissivity based on a jet tracer and some local properties. So very idealized here because we don't have magnetic fields or we don't model an electron population. We can look at how this evolves. Sorry, it's not showing up quite so well, but we can see that what you would pick out as lobes, their location is changing over time, even after the jet has turned off, because of this cluster weather displacing where these are. So the location of your lobes don't necessarily reflect the initial direction of the jet. We've also had a look at the so the lobe that's firing downwards, that gets disrupted because you have this strong interaction with the incoming substructure. The top lobe survives maybe for what, a few times 10 to the 7 years. This is just hydro. So we have ones with magnetic fields now. Yeah, no, that's fine. We've had a look at the energetics. I'm not going to go into too much details on here, but essentially, as has been seen both from estimates from observations and also from other simulations, during the lobe inflation phase, roughly half of the energy remains in the lobes, half of it goes into work done to the environment. We see that the lower power jets are more susceptible to mixing. The higher power jets drive stronger shocks and supply more heating to the ICM through shocks. We can look at this using post-processing shock finder, where we have longer lived, stronger shocks when we have the high power jet opposed to the low power jet. We can also, as I say, look at the mixing. So essentially, this is just looking at the distribution of this jet volume distribution of this jet tracer that we're injecting. And so essentially, as the peaks move to the left, that means you've mixed more. And so over time, the lower power jets move faster and further to the left, indicating that they're more susceptible to the cluster weather and the mixing that happens. The other thing that happens is that the interaction with the cold gas in the center means that the lobe at the bottom here is actually, sort of stunted and more round, while the lobe at the top, the jet propagates more freely, and so you get these asymmetries in the lobe as well. So getting onto the jets with MHD, we're now running the same jets within simulations where there's a cosmological run, we have a very weak uniform magnetic field at high redshift, which we then let evolve and naturally amplifies through cosmic structure formation and feedback process. And then again, at low redshift, we inject the jet, and there's a comparison here. So the run with magnetic fields and without magnetic fields, you can see that when you have these magnetic fields, they suppress the instabilities that you could get with the jet lobes and suppress the mixing. And so the lobes can live much longer when we have the magnetic fields. And we look at this quantitatively as well, just looking at again, the volume of jet material at a particular tracer fraction. Okay. There's then one other. So I put this slide in from a workshop we had a few weeks ago, looking at jet feedback in galaxies, and there was a point that quite often positive feedback can be seen when you have these from observations. It's easier to see positive feedback than it is to really constrain negative feedback because of the timescales. And so we had a look at the star formation rates within the central cold gas when we have these jets at different powers, and essentially we get a higher star formation rate initially with the highest power jet, but then at later times we get lower star formation rates when we've had this initially stronger feedback and a stronger burst of star formation. So when you integrate the star formation over a longer time scale, you find that you get roughly the same stellar mass, and it's actually slightly smaller when we have the highest power jets. And there's also some work from a few years ago with Kostita Zubovas, where we did just generic AGN outflows in a clumpy medium. And one of the things we found is that at low jet power, the feedback isn't strong enough to significantly compress the gas and drive positive star formation. And at high AGN power, it's too effective at disrupting the cold gas and preventing star formation. So there's sort of a middle luminosity at which you get a peak positive star formation, at which you can sufficiently compress the gas without destroying it. Okay, I realize I'm very close to time, so I'm just going to highlight a couple of last things from work that was led by our former PhD student, Rosie Talbot, which starts to bring together some of these models. So it's taking the subgrid accretion disk model where we have the black hole spin evolution and using fits for spin-dependent jet efficiencies, assuming a Blanford-Snaik mechanism from GRMHD simulations, you can determine both the jet power and the jet direction based on the black hole spin and accretion rate. And so this is just an example from some of Rosie's work. This is a jet that's initially just directed along the z-axis. You get this traditional picture with the recollimation, and then you form this turbulent jet structure. In these runs here, we had a circumnuclear disk in here. The jet was initially firing directly into the disk. This leads to this multi-phase outflow that, from observations, you probably wouldn't normally associate with a jet, but more from, say, a wide-angled AGN outflow. But also you can see that the spin, the spin is getting torqued by accretion from the circumnuclear disk, which is bringing the spin towards the z-axis. So this is just a picture from some of these simulations looking at these multi-phase outflow properties. No, that's just from the jet. Yep. Rosie then looked at different phases, so cold gas, warm gas, hot gas, seeing these multi-phase structures. This is really just material that's entrained from the circumnuclear disk, and depending on whether your jet is directly firing into this circumnuclear disk or is it some other relative angle. And then most recently, Rosie's run this model within an idealized galaxy merger. We see again the formation of this cold material in the outflows. And one of the interesting things that happens is that the cold material that forms these outflows then ends up falling back towards and feeding the central black hole, but it has a sense of angular momentum that's perpendicular to the initial spin direction. And in these cases, one of the black holes, the spin is being torqued towards the plane of the disk because of this cold material that ends up falling back and feeding it. And one of the other interesting things is when we have the jet feedback, directed out of the plane of the disk, it's not having much of an effect on the overall star formation, which is different from some of the more traditional simulations of galaxy mergers with AGN feedback. Okay, I think I'm just about out of time, so I'll leave that there. It's not something I've done. Yeah, it's not something I've done from these simulations. So from these simulations, yeah, I haven't looked at this. Yeah, there are a number of simulations from other groups that are including or trying to include cosmic rays, whether these are injected with the jet and are just assumed to be in there, or there are, I think in terms of, yeah, cosmic rays accelerated at shocks and things like this is still, as far as I'm aware, in the more idealized simulations to try and look at these things. It's not something we've looked at. In terms of the thermal conduction as well, I think one of the interesting things that people have been looking at with the thermal conduction is the role of, you have this, what's it called? You have this instability, right, where you realign the magnetic fields, which can prevent thermal conduction from large scales into the central region. There's this question of, how effective this is when you have jets, when you have cluster weather, and if you have a processing jet. And I think the jury's still out on that. And I think, yeah, also with the cosmic rays as well. I think what we have we have some constraints, right, in terms of cosmic ray protons, because we have constraints on the gamma ray emission, which means I don't think you can have a very large population of cosmic ray protons. But then there are also observations, if you combine the radio and X-ray observations of some lobes, you see that you can't explain it all with electrons, but whether that's, yeah, a non-relativistic population of protons or something else, yeah, I don't know. But I think the simulations are moving that way, but yeah, it's tricky. Yeah, that's gonna then, yeah, obviously that's gonna then affect, yeah, how long these things live. And yeah. From first principle sort of thing, yeah. You need spin and you need to get magnetic fields down to the black hole. I mean, there's quite a few simulations from Tchaikovsky, Liska, and they seem to be finding jets in pretty much anything they simulate, as long as you have some black hole spin. Yeah, there's these whole questions around jets in radially efficient and radially inefficient accretion disks. Many of the cosmological simulations, they include, I don't like saying they include jets, they include a mode of feedback that is trying to replicate the impact of jets when it has a low accretion rate, right? So they're making the assumption that you only have these jets when you have a radiatively inefficient accretion disk, but observations show you get jets in both sorts of systems as well. So yeah, I think the key things are having spin and being able to get magnetic fields down to the black hole. Mm-hmm. Yep. I think this is the question we're trying to understand at the moment, right? I mean, in terms of from observations, there are people working in Cambridge looking at the weak lensing, looking at kids and DES data and things like this, and saying, well, if we constrain cosmology to be Planck cosmology, what matter power spectrum do we then need? What suppression do we need to make, to be consistent between, the weak lensing and the Planck cosmology and things like this? I think with the weak lensing, though, there's still a number of uncertainties, and there's differences between, if you compare what you get from one survey to another, there's still differences in what you need to do this. From the AGN feedback side of things, I think at the moment what we need to do is we can look more obviously in cosmological simulations, it's really the large scale effect of the feedback. You want it to do something to the galaxies such that you get a realistic looking population. But we can start looking at the details as well. How do we expect feedback to actually be behaving? And do we get specifics of the feedback right? I think that's a step in the right direction, but I don't think it's the full. Yeah, it's going to take a while. I, yeah, I think this is the direction that things are going. In terms of traditionally, you have, particularly when you have sort of the thermal dump feedback, you calibrate some efficiency parameters until you match, the stellar mass function, and you'll calibrate the accretion until you match the M sigma relation or something like this. I think now there's probably a move from, at least from the people who really simulate AGM feedback, to try and then see what you can learn from the high resolution simulations to inform the lower resolution cosmological simulation. So what do we really need to include to accurately get what the feedback is doing? Because even though we have these models with the high resolution for the jets, you can't have this on really high resolution over the entire cosmic time for the whole system. So we have to try and use the high resolution stuff to come up with models. Sure, yeah. So yeah, I mean, yeah, there's two sides of this. Yeah, there's the feedback and there's the accretion as well. So from high resolution simulations, you can also start to say, well, yeah, if we have these processes acting on this scale, what do you expect to be going on at smaller scales? I think this will be important as well when we want to, really think about the evolution of the black hole spin, which is going to be important for making predictions for LISA and things as well. The other big thing that I didn't talk about that I think still needs more work in the cosmological simulations is dynamical friction, the dynamics of black holes. Many works still just advect the black hole to the minimum potential, so they're moving to the centers of the merger much more quickly than they would in reality. So this impacts, it means you can't really predict merger rates. It also means if you have models where, even if you take a cosmological simulation with a merger tree and you add a delay for the merger, you still don't know what the conditions in the center of the galaxy would actually be like necessarily at the point of the merger. So yeah, I think that's another big area that needs addressing. So if you don't have a binary, so you mean if there's not a binary, you just have a single black hole? Mhm. So this is just naturally arising from. I mean, it would depend on the initial conditions, probably. So this is just naturally arising from the fact that we have a second binary disk that we've put in around this black hole, and then we just let it naturally evolve to give to form the mini disks, and then from the mini disks at the scale of the subgrid accretion disk, you can calculate an inflow rate that then feeds the subgrid accretion disk. Right. I see what you mean. So essentially, in our simulations, it's not really the angular momentum in the second binary disk that's important for the, well, it is important, but we have the angular momentum in the mini disks around each black hole within the simulations already. We do make an assumption. So in the original Fiacconi model, there was a limit on what can be accreted, where you had two criteria. You needed inflow and you needed an angular momentum such that you could circularize onto the accretion disk. So we've lifted that second criteria on the angular momentum, but what we assume is that you need inflow, and then we take the specific angular momentum from the outer edge of the accretion disk. So we're assuming that the material can circularize onto that. We think that approximation is okay, because when we look at the angular momentum profile within the simulations, we see they link up really well. So yeah, the angular momentum in the mini disk at the smallest inner region of the mini disk matches up with the expected specific angular momentum of the subgrid accretion disk. So there's a continuous, yeah.
So you show that you're going to have this problem on the positive floor. When you look at the next floor, it's always negative.
Mm-hmm.
And as you said, in many simulations, actually have this problem. Except in things like, for example, we also got magnetic. So is it the full gravity, or is it a bit of cooling?
Yeah, that's a good question. I mean, there's clearly a different structure in the mini disks and the flows when you have different thermodynamics and different viscosity. So I definitely think that's at play. And there's the original simulations from Rodig that also looked at these things, although it wasn't clear in that case whether there was some numerical artifacts. So I definitely think the thermodynamics is important. There's then the question with the self-gravity. So I think there was a recent paper, the Frankine paper, where they had a massive disk but without the self-gravity. And then it seemed to depend on the viscosity. Yeah. But yeah, I think there's not enough simulation so far with self-gravity and massive second binary disk to, yeah. Thanks.